So in this video, we're going to go over the properties of matrix operations. If you don't know how to carry out matrix operations, then you should probably watch the video that will appear in the top right corner of your screen where I go over carrying out matrix operations. This video might feel like I'm just doing a bunch of properties and not really doing much mathematics or not really solving any problems, but I just need to make sure that you understand these properties, so in the next few videos when we start doing proofs with these properties, it will make a lot more sense to you. Okay, cool. With that, let's go ahead and get right into the video.
So before watching this video, you should know that I plan to make videos covering the entire undergraduate linear algebra curriculum. So make sure that you subscribe to my channel and turn notifications on, and you'll know when I post a new video that will correspond with the concepts you're covering in class. Also, I plan on making review videos that cover these topics at a faster pace. Check my channel if I've released those already, because that will be useful to you if you already know this concept and you don't have to sit around with a more in-depth explanation, and you should get the content across faster. Okay, cool. With that, let's get back into the video.
So the first few properties that we'll go through are the properties of matrix addition and scalar multiplication. I have them written out here, but if you look closely at them, they should look very similar to the properties of real numbers that we've already dealt with. The reason for this being that matrix addition is very similar to real number addition. In fact, if I wanted to add two matrices, let's say adding matrix A and matrix B, all I'm really doing is taking every single entry in matrix A and adding it to its corresponding entry in matrix B. This notation right here, all it's saying is that I'm taking some general entry in matrix A in the ith row and jth column and adding it to some general entry in matrix B that's also in the ith row and jth column. So if this is true, then what this implies is that since these are just real numbers that I'm adding together, I can flip these around and the sum should still be the same. So aij plus bij should equal bij plus aij. And this, if you look closely, is just matrix B plus matrix A. All I'm really doing in both cases is taking a term from each matrix and adding it to its corresponding term in the other matrix to generate a new term in the sum. This is how we write out the notation in mathematics terms, but intuitively it should make sense that matrix addition is commutative, and this is the first property that I have written here. Let me also go and prove the fifth property to show how the proofs are pretty similar. Because if you pretty much can prove one of these, you can prove all of them, since all they're really saying is that you can add general terms in a matrix, and since these terms are just real numbers, all the properties of real numbers still apply here. So let's do the fifth property as well and show how you might prove it. So the fifth property is the distributive property. If I have some scalar constant c and I'm multiplying it by matrix A plus B, all this is doing is taking this scalar constant c and multiplying it by every single term in the matrix Aij plus Bij. Once again, A plus B is equal to Aij plus Bij because, well, we're just taking every single term in matrix A and adding it to B in order to generate the new matrix. So what this is this is just equivalent to, well, since these are just real numbers, we can distribute this using the distributive property of real numbers and get C times Aij plus C times Bij. And this is the same thing as C times A, because Aij represents the general terms in matrix A, plus C times B, because Bij represents the general terms in B. I hope this is making some sense. Aij and Bij just represent the general terms in each matrix, and since they're real numbers, we can pretty much apply the same properties of real numbers to them and get the same results, which are these properties right here. The next thing we're going to discuss is something called a zero matrix. So when it comes to real numbers, we only have one zero. And the reason for this being that we can add any real number to zero and it would be a legal operation. However, when it comes to matrices, we can only add two matrices when they're the same size. So in order to create a zero matrix, we would need to have infinite sizes of the zero matrix. That's why we have infinite zero matrices. for a zero matrix to be defined, it has to be the same size as the matrix we're adding it to. For example, here, if A is an m by n matrix, as I have written right here, if A is an m by n matrix, then the only way that I can perform an operation with the zero matrix where I add it is if the zero matrix is also m by n. That's the only way matrix addition is defined. So here we have our first property where A plus the zero matrix has to equal A. And the zero matrix, since it must follow this first property, just contains all zero terms. For example, if A is, let's say, a 2 by 3 matrix, so 2 rows and 3 columns, and the zero matrix is also 2 by 3, obviously, because it also has to have the same size as A, then this zero matrix must contain all entries of 0. Because that's the only way that we can add these two matrices. That's the only way we can add A and 0, 2, 3 and still get A back. Let me just rewrite this so it's less confusing. So A plus the 0, 2, 3 matrix must equal A again, and I'm just saying that A is a 2 by 3 matrix, and the 0, 2, 3 matrix would look something like this. It would just contain all entries of 0 and be the same size as A. The reason that it contains all entries of 0 is because that's the only way that we can add it to A and still get A back. It also follows this property right here where if you subtract A from A, you do get the zero matrix, because that by doing that, if you subtract every single term in A from itself, then you're obviously going to get zeros in every single position in A. And C times A, where C is some scalar right here, then that would, and if that equals a zero matrix, then either C is equal to 0 or A is equal to 0 matrix. Again, if we have C times A here and we get the 0 matrix, that means either C is equal to 0, the scalar is equal to 0, or A is equal to the 0 matrix. That's the only way we can end up getting the 0 matrix. And the 0 matrix is just a matrix that contains all zeros, and it's the same size as the matrix we're carrying out the operation with, in this case A. I hope that made a little bit of sense. Next, we have the properties of matrix multiplication. Now, these properties, I'm not going to prove them here, and they're not as intuitive as the other properties. In fact, I'm going to prove them in a later video. But for now, all I want you to note is that matrix multiplication isn't commutative. In other words, if I were to have two matrices A and B again, let's say, then A times B doesn't necessarily equal B times A. And you can prove this to yourself by taking two matrices. Let's just say we have A is equal to 2, 7, 3, 2, and B is equal to, I'm just making two random matrices that you can use. If I use these two matrices, I'll see that A times B isn't necessarily equal to B times A. And this is because matrix multiplication isn't commutative. And that basically means that this doesn't necessarily have to be true. This right here. So, since matrix multiplication isn't commutative, you need to keep that in mind. You can't simply multiply two matrices in any order and get the same thing. Matrix multiplication, however, is associative. That means that if we have three matrices multiplied in a specific order, we can multiply either these two matrices first or these two matrices first and still get the same answer. Matrix multiplication is also distributive. So as you can see right here, the distributive property still applies, and it applies to both sides. So we can distribute A to this matrix or C to this matrix over here. It works out a little bit different. If A is on the left-hand side and we're multiplying it by B plus C, we get A times B plus A times C. Whereas if we have A plus B times C, we get A times C plus B times C. So it does work out a little bit different. It's important to note that you can't mess up the order when you're doing distribution, whereas in real number multiplication, the order doesn't matter. For example, by that I mean you can't have C times A here. That's not correct. It has to be A times C, because that's how the distribution worked. If it's on the right side, it has to go on the right side. If it's on the left side, it has to go on the left side when we distribute it. But you can use the distributive property here, and you can multiply the constant by either matrix and still get the same thing here. That's property 4. So the last concept that we're going to discuss is the idea of the identity matrix. And essentially what the identity matrix is it's a matrix which, if you multiply by another matrix, as long as the size corresponds, you get that same matrix back. It's pretty well illustrated right here. So if I have A and I have the identity matrix that corresponds to A, I get A back. Now notice how I said it's the identity matrix that corresponds to A. The reason I said that is because the identity matrix has to be a specific size for the matrix multiplication to exist. And the identity matrix is always square. So the identity matrix is always square. By that I mean it has the same number of rows and columns. Identity matrix is always square. That's important. So since the identity matrix is always square, it always has the same number of rows and columns. However, we need to define an identity matrix so that the operation exists. For example, let's say that A is a 2 by 3 matrix again. If A is a 2 by 3 matrix and we want to multiply an identity matrix on the right, remember, multiplying a matrix on the right and multiplying a matrix on the left give different things because matrix multiplication isn't commutative, like I showed you before. Then let's say I'm multiplying I on the right. It has to have, if A has 3 columns, I has to have 3 rows. So I would be a 3 by 3 matrix. And the reason it's 3 by 3 is because it's square. If it has 3 rows, it has to have 3 columns. Now, so I would write that as I with a subscript of 3 because it has 3 rows and 3 columns. That's the only way that this matrix multiplication can be defined. But let's say that we want to multiply I on the left. Well, if we're multiplying I on the left, then I must have 2 columns. So since it has 2 columns, it also has to have 2 rows. So we say I sub 2. Remember, I changes according to the matrix we're multiplying it with and the side of the matrix that we're multiplying with. That's the only way that I can be defined. That's the only way matrix multiplication can be defined. So just like we had with the zero matrix, we have with the identity matrix that we have an infinite number of identity matrices. Now, what does the I matrix itself look like? Well, in order for the matrix multiplication to produce the exact same matrix we're multiplying I with, we need I to look like a square matrix that has 1s across its main diagonal. For example, I2 would look like this. It just has 1s across its main diagonal. By that I mean from here to here, it just has 1s. I3 would look like this. Once again, it's just a matrix that has 1s across its diagonal, its main diagonal, and has 0s in every other entry. I hope that makes some sense on the reason why we have so many different identity matrices and what the identity matrix looks like. It's always square. Its size depends on which side you're multiplying it by a matrix and the size of the matrix you're multiplying it with, obviously. And the matrix itself has 1s across its main diagonal. And the identity matrix, what it does is it just produces the same matrix again when you multiply it by something. So that's just an overview of a few matrix properties that you'd need to know.
I just wanted to thank you for sticking around until the end of the video. It really does mean a lot to me. If you have any questions, you're welcome to leave a comment and I'll try and respond as quickly as possible. On screen, you should see a link to a playlist containing every single one of my individual linear algebra videos that I made so far and the ones that I would have made in the future. So go ahead and check that out. You should also see my last video. So if you're a little bit confused in this one and want to see the previous concept, you can click on that. And finally, you should see a subscribe button. And if you want to be notified for my future videos and also wanted to tell me that you enjoyed this video, you can do that. Okay, cool. So that's it, and until next time, bye!